This is Professor Serhii Gryshchuk from Ukraine. The talk, representations of solutions of Lamé system with real coefficients via monogenic functions in the biharmonic algebra. Please, Serhii.
Have a nice day to everyone. Thank you very much for the possibility to have a talk at the HyperComplex seminar 2023. My talk is deal with finding Lamé-type system with real coefficients by use of some hypercomplex monogenic functions. Let us to go. We say that an associated commutative two-dimensional algebra B with unit E over the complex field C is biharmonic. This notion was proposed by Kiev's mathematicians Kovalov and Melnichenko in 1981. If in such algebra there exists a biharmonic basis, here a basis satisfying conditions 2, 1. We restrict our attention onto one biharmonic basis, having the multiplication table in the form 2.2, where I is the imaginary complex unit. This biharmonic basis was found also by Kovalov and Melnichenko. This algebra also isomorphic to four-dimensional algebra, which find by study to isomorphism. In the work of Melnichenko, Kiev mathematician, he proved that there exists a unique biharmonic algebra B with non-biharmonic basis E rho. E, this is a unit of algebra. Rho is an nilpotent element, and it connects with biharmonic basis 2.2 by the relations 2.3. Consider the Euclidean norm, and also consider a biharmonic basis, which is a linear span of biharmonic basis 2.2 over real numbers. To any domain D of the Cartesian plane x or y, we associate the congruent domain D sub zeta in the biharmonic plane. In what follows, zeta equals x times E1 plus y times E2, and z equals x plus iy, where a pair xy belongs to D. Every monogenic functions with values which maps domain d zeta to algebra B has expansions 2.4. So we have that we can imagine it as four real functions, U1, U2, U3, and U4. And we also use the following notation: U sub L of phi equals such component, U sub L. Taking into account that every non-zero element of the biharmonic plane has the inverse element, we can define a notion of derivative for such functions phi, similar to the complex case. We say that the function phi, which maps d zeta to B, is monogenic in the domain d zeta if it has a classical derivative at every point zeta from d zeta. It's proved by Melnichenko that a functions phi from d zeta to B is monogenic if and only if its real valued component functions U1, U2, U3, and U4 are real differentiable in D, and the following analog to 5 of the Cauchy-Riemann conditions is satisfied. It is proved by Plaxa and Gryshchuk in 2009 that every monogenic function has derivatives of any natural order in the domain zeta and satisfies the biharmonic equation. Therefore, all real components U sub j in the expressions 2.4 are biharmonic functions. At the same time, every biharmonic functions in a simply connected domain D is the first component in the expressions 2.4. So we can fix any biharmonic functions in the simply connected domain and find all monogenic functions by the formula 2.6. Also, we described all monogenic functions where the left part equals to 0, and these monogenic functions can be we can see such functions by the formula 2.c. So this is a polynomial at most the second order. If a isn't equal to 0, this is a polynomial of the second order with respect to HyperComplex variable zeta. If a equals 0 and k minus b(e2) isn't equal to 0, this polynomial of the first order, and so on. So we consider a system, Lamé-type system 3.1. Here, x, y, this is a point of our domain D. P is a real number, except of 0, and theta equals the partial derivative of U with respect to x plus the partial derivative of v with respect to y. We mean by solution of the system 3.1, it's regular solution. Here, a pair of twice continuously differentiable functions satisfy this equation. Equation 3.1 is of elliptic type if p isn't equal to -1, and when p equals -1, it is generating. At the same time, if p has some values having physical value, the system 3.1 is a Lamé system of equilibrium equations of isotropic plane theory of elasticity with respect to the vector displacements u and v. And by physical meaning, we have that p is more than 1/3. 1/3. This is for this case when system 3.1 is an equilibrium system of isotropic plane elasticity. If p isn't equal -1, then we can prove by the similar way as for isotropic case that function u and v, components of solutions of system 3.1, are biharmonic. And if p equals -1, we claim additionally that we are looking for solutions of the Lamé system 3.1 satisfying such conditions 3.2. And we call such solutions as biharmonic solution of Lamé system. Yes. by the domain D of the Cartesian plane x or y, we mean such domain which is congruent to such domain of the complex plane, and we assume that this domain is also simply connected and not necessarily bounded. And the main result is the following. A general solution of the Lamé system 3-1 with p isn't equal to -1 is expressed by the formulas 3-2. Here we see that the first component of solution is the first component uy, u of u1. Here this is the first component u1. And the second component v equals the first component of such linear combinations. A, this is hypercomplex number of the algebra times onto monogenic function phi and plus q. Q, this is also a polynomial of the second order. A gives by this such formula, P by the following formula. Here C, M, this is arbitrary real numbers. Yes, and B, the previous formula, and B1 and B0 are arbitrary elements of the algebra. And a general biharmonic, this is for case p except of -1. For p equals to -1, we have a similar formula for biharmonic solutions, but for v, we have an extra term, IB over 6 times zeta to the power 3. Yes, the main the sketch of the proof is the following. We are looking for this solution u and y as the first components of the appropriate monogenic functions. We can do it by the fact that for simply connected domain, any biharmonic functions can be defined as the first component of such for the following biharmonic functions. Then we obtain relations for differential operated at the domain, transform to the Lamé system and go to the system 3.6. Here we, at the left hand, we have first component of the second derivatives of our monogenic functions. And we have descriptions. If first component of monogenic function equals to 0, then this monogenic functions equals to such polynomials p, which is the polynomial at the most second order. And p with tilde, this is a similar polynomial. Then, further doing some transformation, we obtain a relation between such polynomials. Here. And this is the following and then we obtain such formula for polynomials p. Because this is good that we have relations, but for our solutions we need only formula for polynomials p. Then transforming and replacing for our functions u and y, we obtain such relations 3.20 between our monogenic functions, which generates our solutions. Then integrate twice these equations, we have such solution between function monogenic phi and f. And then we prove that these monogenic functions generate a general solution of our Lamé system by the formula 3.6. 3.6. So we see that for the case pair -1, we see another extra term, EB over 6 times zeta to the power 3. This fact has some analog, because if we are looking for the polynomial solutions of the Lamé system, and similar result also obtains from another researches. So here we have some natural analog. And also we can obtain corollaries when we find components of the equality 3.6. We obtain such formulas. Here we see that U equals to the first components of our monogenic function phi. The first component of the solutions V equals some linear combination of the second and the third components of our monogenic function, and plus these polynomials, complex polynomials, also at most the second order. And of course, in our formula we have general formula. Of course, except with the function phi monogenic function, we can replace it with the product C times phi, where C is any non-zero element in B. Because if we multiplied any monogenic functions to any element of algebra, non-zero algebra, we also obtain monogenic functions. So we taking fixed element, we consider different formulas. For example, if we take for C the second element of the biharmonic basis, we can see the formula for our solutions as the form 3.30. Here we see such formulations that the first component U equals to the third component of our monogenic functions, and the second component of solution V equals linear combination of the first and four component, and plus also some polynomials. This is the previous polynomials plus Q1. Yes, polynomials Q1 plus such extra term. So we can see that doing multiplication by different elements, we can do that first component of solution U equals to some component UR of UL of monogenic functions, and at another solution we obtain linear combination of some another components of monogenic function, and plus some extra polynomials. Thank you very much for attention.
Okay, thank you, Professor Gryshchuk, for your interesting talk. Any question or comments? Okay, I have a question. are the representations for solutions of Lamé system represented in the main theorem and in the corollaries are completely equivalent or not?
We have different representations. Corollaries gives us another representation. We have different representation.
Consider the previous corollary. Yes, what these representations is equivalent.
Equivalent in the sense that they gives all solution. You mean this sense equivalence? That they gives all solution. In this sense, of course, they're equivalent because
okay. Any solutions can be represented in
different form of representations.
Okay. Okay. Thank you very much.